Let's continue to look at inverse matrices, and now let's look for inverses of 3 by 3, 4 by 4 and larger matrices. We also have a technique to find the inverse of a larger square matrix, a 3 by 3 or a 4 by 4, or a higher number, or a higher number of rows by the same number of columns. What we actually do is we start off and we write what's called an augmented matrix. We take our original matrix, and to the right of that we put the identity matrix of appropriate order. And then, having done that, we carry out row operations. We can take a row, and to it we can add a multiple of another row. The reason for doing this is to create zeros in key positions, and we do that until the matrix on the left is upper triangular. That is, all entries below the main diagonal are 0. The matrix on the right will now be moved away from its original form, and then we carry out more operations, more row operations, until the matrix on the left is a diagonal matrix. That is, all entries above and below the main diagonal are 0, and then we'll divide each row by the coefficient on the left, so that the matrix on the left is now the identity matrix, and if we do the row operations properly, then the matrix on the right will now be the inverse matrix. So whatever we do to the matrix to turn it into the identity matrix, doing the same thing to the identity matrix turns it into the inverse matrix. So let's see this in terms of, say, a 4 by 4 matrix. So here we have a 4 by 4 matrix, 4 rows, 4 columns. There doesn't look anything particularly special about this matrix. We form the augmented matrix by writing the 4 by 4 identity matrix on the right here. So that's our augmented matrix. We want to carry out row operations to turn what's on the left into the identity matrix. We carry out the same row operations on the right, and we'll turn this into the inverse matrix. So here's our augmented matrix. Now, we look to find zeros in a particular order. We would like, firstly, to get zeros in the 3 positions here by subtracting multiples of the first row. So row 2 we will replace by row 2 minus twice row 1. That'll give us a 0 here. Row 3 we'll replace by row 3 plus 3 times row 1 to give us a 0 in this position. And then we'll take row 4 and replace it with row 4 minus row 1 to get a 0 here. You see, we get zeros here. The entries in the rest here change, and we get non-zero entries here. So that's our first set of row operations. Then we look to get zeros in the 2 positions here. And we can take row 3 and add on row 2 to get a 0 here. We can take row 4 and add on row 2 to get a 0 here. The entries here will change. We get non-zero entries here. The only entry now preventing what we have here from being upper triangular is this entry here. So we'll take row 4 minus twice row 3 to get a 0 here. The entries over here change accordingly. But here we have an upper triangular matrix and, well, we have a lower triangular matrix on this side. But now we want to get zeros above the diagonal. So let's take row 2. So let's take row 1 and we'll subtract off twice row 2 in order to get a 0 here. The other entries in row 1 will change. So we've got a 0 here. Then we look for zeros in the 2 positions here. So we'll take row 1 plus twice row 3, row 2 minus 3 row 3. Again, entries in row 1 and row 2 will change. And then we'd like zeros in the 3 positions here. Row 1 minus 8 row 4, row 2 plus 13 row 4, row 3 minus 4 row 4. We get zeros in the 3 positions here, and then of course the other entries on the right will change. Now we have a matrix with 1s down the main diagonal, zeros everywhere else. Now we've had a little bit of a bonus here in that we've arrived here with 1s down the main diagonal. If we'd had numbers other than 1 down the main diagonal, it would simply be a case of dividing each row by the entry here. But we're dividing by 1, so what we have here on the right becomes our inverse matrix. So we've worked out the inverse matrix here, and of course we could check by multiplication that it's correct. It's useful to draw attention to the order in which we created zeros. Once we have a 0, once we've identified where we want a 0 and created a 0 here, we need to look after it. Sometimes you might get other zeros which happen to occur elsewhere. Those need to be treated as a bonus, and it might be you end up having to destroy those zeros later. But the ones that you have worked hard to create, you should work hard to keep. So in here, you can see, well, I mentioned X for any of the entries on the left. We'll also mention Y for any of the entries on the right. But where we have 1s and 0s, those are mentioned as 1s and 0s. We look for zeros in the 3 positions here by subtracting multiples of row 1. Then we look for zeros here in the 2 positions here by subtracting multiples of row 2. Then we look for a 0 here by subtracting a multiple of row 3. So you can see we're upper triangular on the left, lower triangular on the right. But then we look to create a 0 here by subtracting multiples of row 2. Those 2 positions we want to become 0 by subtracting multiples of row 3. And then the 3 positions here we want to become 0 by subtracting multiples of row 4. And then we'll have on the left something with entries which will not be 0 down the main diagonal. And we divide by each line by the relevant entry here, so we have the identity matrix on the left, and on the right that will give us our inverse matrix. Now if our original matrix was singular, then at some point we would end up with a 0 down the main diagonal, and the calculation would grind to a halt. Let's use this technique to find the inverse of the matrix here. The 3 by 3 matrix, 1, 2, minus 1, 4, 9, minus 1, 1, 3, 3. So here is the original matrix that we want to find the inverse of. I've deliberately left the right bracket off so that I can add on the identity matrix here, 1 0 0 0 1 0 0 0 1. So we've added in the identity matrix here. This is now what we call the augmented matrix. Now we'd like to turn the left-hand side into the identity matrix. We'll look for zeros in the two positions here and here. I'll take row 2 and subtract off 4 row 1. I'll take row 3 and subtract off row 1. So row 1 stays the same. 1 to minus 1, 1, 0, 0. Row 2 minus 4 row 1. 4 minus 4 times 1, 0. 9 minus 4 times 2, 9 minus 8, that's 1. Minus 1 minus 4 times minus 1, minus 1 plus 4, that's equal to 3. 0 minus 4 times 1. 1 minus 4 times 0. 0 minus 4 times 0. And the bottom line, row 3 minus row 1. 1 minus 1. 3 minus 2. 3 minus minus 1. 0 minus 1. 0 minus 0. 1 minus 0. So after one set of row operations, we have zeros here and here. We'd now like to find a 0 in this position. So I'll take row 3 minus row 2. So the first two rows stay the same. And then we have row 3 minus row 2. 0 minus 0. 1 minus 1. 4 minus 3. Minus 1 minus minus 4. That becomes 3. 0 minus 1. 1 minus 0. On the left, we have an upper triangular matrix. On the right, we have a lower triangular matrix. The next place where we want a 0 is here. And we'll achieve that by taking row 1 and subtracting off twice row 2. 1 minus twice 0. 2 minus twice 1. Minus 1 minus twice 3. 1 minus twice minus 4. 1 plus 8. That gives us 9. 0 minus twice 1. 0 minus twice 0. The bottom two rows stay as they were. Finally, we would like zeros in those two positions. And we'd like to achieve that by adding or subtracting multiples of row 3. So we'll take row 1 plus 7 row 3. We'll take row 2 minus 3 row 3. So when we do that, 1 plus 7 times 0, 0 plus 7 times 0, minus 7 plus 7 times 1. Minus 7 plus 7. 9 plus 7 times 3. 9 plus 21. That gives us 30. Minus 2 plus 7 times minus 1. Minus 2 minus 7. That's minus 9. 0 plus 7 times 1. Now, row 2 minus 3 row 3. 0 minus 3 times 0. 1 minus 3 times 0. 3 minus 3 times 1. 3 minus 3. Minus 4 minus 3 times 3. Minus 4 minus 9. That's minus 13. 1 minus 3 times minus 1. That's 1 plus 3. 0 minus 3 times 1. And the bottom row stays the same. We should at this point have a diagonal matrix on the left, and indeed we do. In fact, we have the identity matrix on the left. If we'd had non-1 entries in this diagonal, we would simply have divided the relevant row. So strictly speaking, we take row 1 and divide by 1. We take row 2 and we divide by 1. We take row 3 and we divide by 1. Of course, everything stays the same when we divide by 1. So this is now our identity matrix on the left. What we have on the right is the inverse matrix. So we can now say that the inverse matrix A inverse will be what we have on the right here, 30 minus 9, 7, minus 13, 4, minus 3, 3 minus 1, 1. This is our inverse matrix, and of course we could verify when we carried out multiplication involving this and our original matrix, we would return the identity matrix.